In my previous video of this project, I designed and built a 14-foot catamaran from scratch. In this video, we're going to do a lot of testing to get familiar with the performance of this boat, and then I'm going to try and boost its performance even higher by adding a big hydrofoil to the bottom. So stick around for that. But first, a quick recap of this project. My previous electric boat was far from optimal. It was just two e-foil motors plopped onto a 13-foot planing hull. This hull was designed to go fast, not slow, so the boat was pretty inefficient at the slow, solar-powered cruising speeds that I was driving it at. This new catamaran design was partially inspired by rowing shells. These long, narrow hulls would probably only require like 10% of the power that my old boat did to travel at the same speed. My new hulls are nowhere near as long and narrow as a rowing shell, but they're definitely a step in the right direction. To build them, I started by 3D printing dozens of hull segments out of foaming, lightweight PLA and then gluing them all together. This method takes a lot more time overall, but probably a lot less manual labor than if you were to carve them out of foam. And you end up with a shape that's dimensionally identical to the CAD model. After the hull cores were assembled, I lined them with unidirectional carbon fiber for strength in the lengthwise direction, and then plane weave carbon fiber to make up the majority of the skin thickness. And then I built a frame out of wood to hold the hulls together, and it had foam in the middle for a deck to sit on. And that also all got wrapped in carbon fiber for strength and durability. The first test with 350 pounds of meat and bones on board showed that 350 pounds is a bit much for this boat because we were riding pretty low in the water, but it did end up working just fine. We were able to hit 10 miles per hour while powered on 24 volts, but I should add, speed was never the goal with this project. The goal was efficiency. So that's a recap of the previous video. Now on to the new stuff. On this day I was just out having a little fun, getting some nice drone shots, and getting a feel for what these hulls can handle.
There is just zero wind today, so this is not a very good rough water testing day for these hulls. But we do have a little boat wake coming up here. That's a very small wake, but so far so good. No other boats out here. What gives? I want to jump a wake.
Here I discovered that you really need to slow down for boat wakes because these hulls bottom out pretty easily. I didn't design this thing to be a rough water boat. I designed it to be a low to the water experience, kind of like my powered paddleboards in the past. But in hindsight, I probably should have made the hulls a little bit taller, but oh well, I can always extend the deck up higher if I want to later on. I also measured the motor data on this day, and when we're on a 24-volt battery, we're doing about 1150 watts per motor. Interestingly, the boat was 200 pounds lighter than during the previous test, but it only went 1 mile per hour faster. This kind of speaks to how great displacement hulls are for transporting heavy payloads. Weight just doesn't affect them all that much. It's worth noting that the hull speed of this boat is 5.7 miles per hour or 5 knots. And even on the 24-volt battery, I'm going nearly double the hull speed. For those who don't know, the hull speed is the speed at which most displacement hull boats start to become really inefficient. If you exceed the hull speed, the boat is basically always climbing up the wave created by the bow. This takes a ton of power, so the majority of displacement hulls simply can't exceed their hull speed. But if your hull is super long and narrow like mine, the bows create a smaller wave, so it takes less energy to climb up it. If my boat were wide like this, it probably would not be able to exceed the hull speed, but the hulls are narrow, so it has no problem at punching past the hull speed. Later in this video, we're going to run the boat on a 48-volt battery and see if it'll go even faster than 2 times the hull speed. So the next day I set out to find a more efficient set of propellers for this boat, since these old SLS printed props from the electric Boston Whaler days are likely far from efficient. I'm going to be testing different size variants of the prop that won the RC Test Flight Propeller Design Competition last year. This design was a collaboration between Friendship Systems, who makes CAD programs specifically for CFD and fluid dynamics, and AirShaper, who makes cloud-based CFD software. So they teamed up and used a machine learning AI iterative design process to optimize the propeller geometry for the given motor that we were using, and this is what it spit out. Now, I don't have torque or efficiency data for the FlipSky 65121 motor that I'm using on this boat, so I'm just going to use the trial and error method to test different sizes of the winning propeller design and see which one results in the lowest energy consumption. So, I SLA printed 3 different size variants out of gray resin on the Formlabs Form 4. Some of them were too big to fit in the build volume, so I printed the blades separately from the hub with dovetailed joints so they can fit together easily. If anyone wants access to the CAD files for these props, or the hulls, or the motor mounts, it's all available for free of charge at the Onshape link in the description. Onshape runs in your internet browser, so you don't even need to install anything. Just click on the links and you'll have access to the native CAD models. So I'm going to be using this thing to measure the efficiency. It's called the Megan from Voyage Systems, and it reads CAN bus data
from the motor drivers. Right now I only have it connected to one. I only have props that spin in one direction, so I'm just going to be testing the efficiency of one motor, not both combined, but that should still give us a good idea of which props are best. And this number in blue here is our efficiency in watt hours per kilometer and watt hours per mile over here. So right now I'm super efficient, only 0.5 watt hours per mile, because I'm basically just drifting downwind here. It's supposed to be calmer today, but we got a little bit of a breeze, so I'll try and do my test runs perpendicular to the wind so that it doesn't have as big of an effect. And this phone is just connected to this over Bluetooth, so nifty little device. You can get all the data you need from your Vesk. And I'm powering this motor off of this giant Lifepo4 deep cycle battery. And the really cool thing about this battery, let me show you here. There's an app and you can connect to the battery via Bluetooth, and you can see the state of charge. The MOSFETs are on or off, the current, the voltage, the individual cell voltage. I have another one of a similar size over here in the hull, but this one does not have the Bluetooth. But yeah, I designed these cutouts in the hulls specifically to fit this size of battery. So if you remember back to my towboat video where I built that big RC boat to tow me on the hydrofoil, I was using these props. They were CNC machined by PCBWay. They're stainless steel, super strong. This propeller won the propeller design competition because, okay, for one, the propeller geometry is really efficient, but what's almost more important is that it was really well matched to the motor that I used for the propeller design competition. And that is not this motor. So just because this propeller won the competition does not necessarily mean that it's gonna work well on these motors. But I'm gonna try it anyways, and then I have smallest, bigger, bigger, biggest. So I'm gonna test all these and see if I can kind of narrow in on the optimal size of propeller, of this propeller design at least, for this motor.
On this day, I was a little too excited and I didn't think enough before I started testing. I ended up testing each propeller at the exact same throttle level. That might sound okay at first, but the problem is my motor drives are actively controlling the RPM of the motor, so I was effectively testing each prop at the same RPM and measuring the resulting efficiency. It turns out you can't just do that because each size of propeller has a different amount of rotational resistance and will therefore result in a different amount of power consumption. For example, the biggest propeller has more resistance than the smallest one, and since they're both being spun at the same speed, the bigger one is going to pull more current because it needs more torque. So as a result, I was accidentally putting more power into the bigger propellers, which of course resulted in a higher top speed, and therefore a lower efficiency, because efficiency drops pretty significantly as your speed increases.
Now it is true that this one has the pointier rear end compared to this, but I'm still pretty confident that that doesn't make enough of a difference to skew our efficiency measurement.
Let's say you buy a motor like this, and you want to use this exact same propeller on it. Well, guess what, dear viewer? You're in luck, because thanks to today's video sponsor, you can. PCBWay will machine these propellers out of stainless steel just for you, and all you have to do is send them a boatload of money. After tax and everything, I think a pair of these were around $1,000. But stainless steel is super overkill. 3D printing them out of aluminum would have been much cheaper. That's probably what I should have done instead of CNC. In addition to 3D printing and CNC machining, PCBWay also does laser cutting, injection molding, and of course PCB fabrication and PCBA assembly. Look at this giant set of PCBs I just had PCBWay make for an upcoming project. Can you guess what it is? I also had them laser cut these copper strips for another upcoming project. It's so much more convenient than having to do it on my own CNC machine. Just send them the drawing and a few days later the parts show up. Definitely check out PCBWay for all your prototyping and manufacturing needs. Use this code to get $10 off orders over $30. And big thanks to PCBWay for their continued support of this channel.
Look at that chicken. Let's go say hi to these ducks. Here, duck. Duck, duck, duck. Quack, quack, quack. Now I'm headed to the other side of the lake in search of rougher water so we can do some rougher water testing with these hulls. These are by no means choppy conditions, but it's a little rougher than before. Now we're at full throttle, 18 kilometers per hour. Yeah, no problems here. 19 kilometers per hour. At full throttle, my estimated run time is 2 hours and 18 minutes. Wowee, look at that. These people have a seaplane in their backyard. That's the dream right there. Whoa, big duck coming in hot. Such a great boat.
So the only sound data I got on this day was a test where I measured efficiency at different speeds. The hull speed is right here. It's pretty cool. We can actually kind of see how the efficiency gets worse and worse as we approach the hull speed. And then once we break that, it kind of starts to ease a bit. That's about what you would expect according to the old maritime textbooks. The next day, I set out to rank the propeller efficiency in a more valid way.
So what I'm gonna do today is control the speed of the boat. So I threw this Pixhawk autopilot on here, running ArduPilot. I got a little GPS up there I just taped in place. So now I can control the boat's speed with high precision and look at the actual watt hours per kilometer of each propeller. So this should give us much more accurate results than I got last time. Last time I did zero planning. I'm using the trim on the radio to really precisely set the throttle so that the set point is 1.5 meters per second and 3 meters per second. I'm testing at 2 speeds. The gyros and accelerometers in this flight controller are updating so fast that even if I move my hand, you can hear the motors change RPM to try and compensate for that. Pretty crazy. We got quite high bandwidth control. The GPS itself isn't sensitive enough to get that high bandwidth of velocity data, but the flight controller is fusing in accelerometer data to get a super accurate and high speed velocity estimate. Pretty crazy, man. This whole boat is just a big robot. Right now it's holding 1.5 meters per second very precisely, and I'm looking at the watt hours per kilometer here on the Megan.
So I did all the tests and ran the boat at 2 different speed set points per propeller. The RD Pilot flight controller was also able to keep the boat going in a perfectly straight line, which was important because I was only measuring efficiency from one of the 2 motors. So if we were turning due to the differential thrust at all, it would have seriously skewed our results.
3.5 watt hours per kilometer. Well, I'm glad I decided to do the tests again because the results are pretty different. It looks like the stainless steel propeller is still the most efficient at high speeds at 3 meters per second, but at slower speeds at 1.5 meters per second, the smaller SLA propeller is the most efficient. So the smaller blades are more efficient at high speeds, the bigger blades are more efficient at low speeds for this particular setup. So now I just have to kind of figure out what my most common cruise speed is going to be and select the propeller size to match that. I think I'll probably end up going faster since these batteries can power this boat for so long. My average speed will probably end up being higher because I normally am not out for 50 hours, so I don't need to try and conserve power. So I can go faster. So I'll probably select the best prop for the 3 meters per second. So that's our stainless steel propellers. Good science. There's no wind. I'm just sitting here eating fake Cheetos. It doesn't get much better than this. I'm also doing heading hold mode right now, and our heading has been 304 degrees for quite a while, and it's just holding a perfectly straight course. Ooh, I should do a time lapse. I'm gonna put the camera right here, put it in time lapse mode, and we'll be able to see how straight of a line it makes. There is just no wind out here. It is so nice. Oh, there's so much pollen in the water right here. I'm gonna take advantage of the fact that it's so calm and do a speed versus efficiency graph. So I'm starting off super slow and I'll gradually raise the throttle until we're at max speed. And then we'll be able to see a nice curve to show our efficiency versus speed.
I'm doing this test a little differently than the last one where I just manually recorded all the data. The Megan records all the data internally, and then you can access it over Bluetooth on your phone and just text it to yourself. Then I imported it into Google Sheets as a CSV, and the graph looked really bad, but after a bit of filtering it looked like this. We can still kind of see the hull speed hump, but it's not as obvious as before. So today we are trying to sail this is not working. I'm going straight sideways. I need to hold it way out in the front to try and get the, oh shit, it's going fast. Oh. Come on, go. Okay, now it's starting to move forward a little bit. Yeah, we're going. I don't think there's any chance that I'm gonna be able to go upwind with this thing, but yeah, now we're going. I gotta steer by shifting my weight around on this deck, like fore and aft wise. Oh wow, we're moving now. We're cruising. Yeah, now it's pulling. Need more wind. If you didn't know, this is one of those wing foil wings they use for wing foiling. We were hoping these hulls would have enough lateral resistance as to where we wouldn't need a centerboard, but it kind of seems like we do need a centerboard, or at least in super light winds like this. Maybe in stronger winds it would have worked better, I'm not sure. I have to get all my weight on the back. I think for these wings to really work, you need a lot of wind. They're just so much smaller than sails. So I don't have a rudder on this boat, but I can still kind of turn. Those who have never windsurfed before probably don't know this, but you can pretty easily turn upwind or downwind just by moving the wing fore or aft. The problem with this boat is it turns really poorly in the first place, and the deck isn't long enough to be able to move the wing fore or aft very much, so the turning authority is quite limited. Later we tried this wing with a real windsurf board and it was much more functional. We're doing it. I get an otter pop if I can make it to the far shore and back. Uh-oh.
I'm coming in hot. Woo, you owe me an otter pop. Oh yeah, there you go. Oh man, you're ripping.
And a windsurfer with an actual windsurfing sail was even better. Who would have thought? Definitely a lot harder to learn though. Now for the opposite of sailing. On this day I tested out 12S batteries for the first time. This gives us around 48 volts and it sure does make a big difference. We were able to get up to 3100 watts per motor. Unfortunately I didn't get a good speed measurement on this day, but it did feel a lot faster. Now for the real fun stuff. I drilled some holes in the deck and bolted on this knockoff Axis 1401 hydrofoil. For those who don't know, these are usually used on one of those things that you ride around on.
Today I'm wanting to do an efficiency test with and without this big hydrofoil here, but I came out and it's choppy. I was hoping it was going to be calm today, so I'm going to go up to the I-90 bridge over there and try and take refuge from the wind right on the downwind side of it. I think the water will be flatter over there. So to set the expectation here, I'm not expecting the entire catamaran to lift out of the water on the hydrofoil. I'm hoping that it'll just support the majority of the weight, but the hulls will stay in the water for stability. Now there's a chance we could entirely lift out of the water, and if that happens it'll be pretty cool, but then I would have to try really hard to actively balance the whole thing by shifting my weight around. So I don't know that that'll happen, or if it does happen, I don't know if that'll work, but that's kind of why I'm leaving on this horizontal stabilizer here. If I was 100% sure that the hulls are going to stay in the water, I would take this thing off. We only really need the lift from the main wing, but since just in the back of my mind I'm like, okay, yeah, that would be pretty awesome if we were completely foiling. For that reason, I'm going to leave this horizontal stabilizer on. If I did get the hulls entirely out of the water, I wouldn't be able to go very high because the motors will just pop out of the water. They're probably only like maybe a foot down there. Yeah, it's a good bit calmer over here. The only problem is there's a ton of traffic noise, so sorry about that. So for this rigorous scientific test, I'm going to do one pass at 50% throttle and then another pass at 70% throttle. So two different speeds. And then we'll look at the recorded GPS speed on the Megan here from with and without the foil. And we'll see which one results in a higher top speed. Going at a pretty good clip, doing 12 kilometers per hour of speed. Making a nice looking wake back there. 24.7 watt hours per kilometer. Now I gotta try and screw this giant hydrofoil onto the bottom. That's gonna be a little tricky. Okay, I also forgot one of the bolts, so that sucks. Where's that hole? There it is. Okay, I'm swimming now.
Eventually I got the hydrofoil mounted onto the deck, pushed it out past the weeds, and it was time to start the test.
Man, so far it seems like the foil's making it much worse. So we're at 8 kilometers per hour. I don't see any seaweed hanging off of it. Dang, what gives? I don't notice the hulls being any higher out of the water than they normally are. Yeah, it looks pretty average to me. Here we go for the 70% throttle run. Oh, we're flying, holy sh! Yeah, the hulls are lifting out of the water. Woo! The fronts of the hulls are just barely coming out, and the backs of the hulls are still down, so I gotta move my butt forward a little bit. Oh shit, this is awesome. Wow. Okay, I think we could use a little bit more throttle, but okay, the back of the hulls are still pretty significantly in the water, so the fronts are significantly more out of the water though. That is so cool. The hydrofoil works. I was afraid that it wouldn't be at the right angle of attack, but it definitely is. Okay, so we're at 12 kilometers per hour and we're at 28.5 watt hours per kilometer. Oh, and we are gonna run into the rowing team here. Okay, now I'm just gonna do a little bit of experimentation here to see what kind of throttle levels I can safely go at. This is where things get exciting. Whoa, the fronts of the hulls are completely out of the water. Oh yeah. So I gotta shift my weight further forward. I'm gonna press on even faster. Oh! Oh! Oh, I flew! Wow! Oh, the Megan got all wet. I hope this thing is not waterproof. I know that for a fact, actually. There's exposed electronics under there. Yeah, my weight's just too far back. I can't scoot it forward enough. Okay, that should help a little bit. The danger is if I'm too far forward, I could nosedive, which would be really sketchy. Here we are. The holes are, oh, okay, oh! That did not sound good. I wonder what that was. Okay, well, the foil, oh man. Oh, that doesn't look too great. I'm like squishing the foam on one side. Damn, I gotta get that fourth bolt in there. Shit.
So I went back to the boat ramp, got the bolt in there, and then it was back out on the water.
Oh, this might be sketchy.
Here we happened to encounter the wake from a surf boat, which actually ended up being a great test.
Honestly though, like this boat, before the hydrofoil was on it, it would have just gotten so swamped on that wake. So the hydrofoil definitely does something.
That works way better than I thought it would.
Yeah, it works great. I'm so surprised.
But it was still too tail heavy to really hit high speeds, so I decided it might be good to try with an extra body sitting in front of the foil's center of pressure.
So now we got Lucas here. How much do you weigh, sir?
200.
As you can see, the holes are very low in the water. So let's see if this foil can get us up a bit. Give us more freeboard, is that what it's called? Man, it's calming down. I did not need to wake up at 5 a.m. Our front hull is submerging.
Very smooth.
It's, yeah, super smooth. Our okay, I'm gonna go a little faster. Yeah, I think our center of gravity is decent.
Feel that lift.
Yeah, we're just skimming, man. This is sick. Oh wow. Here's some waves to test. Our tails are still in the water quite a bit. Oh yeah, here, perfect. Here's some waves.
Yeah.
Look at that, just bouncing right over them. Okay, now the submarine.
Even with both of us on there, sitting as close as possible to the front of the deck, it was still too tail heavy to get the pontoons to rise symmetrically. I think if we can keep the boat more flat, then the foils will be operating at a more efficient angle of attack, and the tips of the hulls that are touching the water will have a longer waterline length, so that should make it more efficient.
Dang, it's still too tail heavy. I think we should try taking off the horizontal stabilizer. It's pushing down in the back, which is making it pitch up more. Hi, baby goose. That's it. That's our horse dab.
Unfortunately, removing the horizontal stabilizer didn't seem to change anything. It still wanted to wheelie. Don't forget about the science I did earlier this day. I crunched all the VESCA data that was recorded on the Megan, and this is what we get. On the left side, we have speed. It's pretty obvious that the hydrofoil results in a lower top speed, both at 50% throttle and 70% throttle. On the right side, we can see that the addition of the hydrofoil results in higher energy consumption for a given propeller RPM. That means the foil is adding drag. But how can this be possible? Everyone says hydrofoils are so super efficient. The best explanation I can come up with is that hydrofoils are pretty efficient. But do you know what else is pretty efficient? A long, narrow displacement hull, like mine. They're probably even more efficient than the hydrofoil, or at least at the lower speeds that I was testing at. If we were to run the test at an even higher speed, it's possible the hydrofoil could become more efficient than the displacement hulls.
So today I've got my smaller foil on board since we almost kind of sort of cracked the big high efficiency foil. Oh yeah, I think I forgot to tell you. I noticed these small cracks on the bottom, so I think we overstressed this thing a little bit too much. But anyways, this one is more of like a wake foil. It's made to be more agile and stable versus just like the other one's just made for pure efficiency. So I don't think we're gonna get as much lift out of this foil, but I have it moved back by about a foot or so. So it should be lifting the boat more on the center of gravity, and we should be able to get the hulls to come out of the water a little bit more symmetrically. So hopefully that does something with the efficiency. I don't know, maybe it'll help. But I'm just gonna run the same test that I did yesterday, and then we'll check out the numbers. I'm doing 2 passes for each test run. I'm going upwind and downwind, so hopefully that'll even out. So I'm adjusting my weight here so that the bow and the stern are about the same height out of the water. Now I'm just trying to find the highest possible throttle set point that allows me to foil without leaving the water. That's pretty good right there, man. Wow, yeah, the bows are just barely touching, maybe a tiny bit more.
So on this day, I ran the test at 2 speeds again, but this time the high throttle run was at full throttle. I chose to do this because even at full throttle, the hulls were still touching the water. So that goes to show this smaller wake foil wing has quite a bit less lift than the high aspect ratio foil I was using yesterday. So I ran the test runs with and without the hydrofoil attached, and here's the results. At 75% throttle, we were still able to go a tiny bit faster without the foil. But at full throttle, there was basically no difference in speed. So this suggests the foil might actually help more at higher speeds. If we look at energy consumption over here, at 70% throttle, the boat was more efficient without the foil. But at full throttle, it looks like the foil actually made the boat more efficient. So why could this be? Well, our top speed at full throttle is 18.6 kilometers per hour or 11.5 miles per hour. And that's just right about here on the efficiency versus speed graph we made earlier in this video. And as you can see, the hull gets way more inefficient at that speed regime. So I think the addition of the hydrofoil was more efficient at full throttle because its efficiency curve probably looks more like this. It doesn't start to skyrocket after 16 kilometers per hour like the hull's efficiency curve does. So my big takeaway from this is that the addition of the hydrofoil is really only helpful at higher speeds where the normal hull starts to get super inefficient. At lower speeds, all the foil really does is increase the wetted surface area and therefore increase drag, so it's not as beneficial. I have now rewired the batteries so we're on 12S instead of 6S, so we have double the voltage. I'm not actually sure if this will make us go any faster though, because the ERPM limit is set on the motor drives for 6S, so I might need to increase that. But there is a chance that we'll get a few more miles per hour and maybe get up on foil better, so we'll try it out. That's pretty fast. I don't know if it's any faster. I'm repinning this connector. I need CAN bus so that I can increase the ERPM. I have this wire very jankily crimped together. And it's working, we got power, woohoo! So now we can go to the expert tab, go all the way down, max ERPM, set that shizzle to 9,000, baby. Now I'm out in the middle of the lake, there's a lot more waves out here, so I'm gonna do some rough water testing with the foil. Oh yeah, this is great. Man, yeah, the bows just ride right through the waves. This is definitely much better than with no foil. Let's try and go a little faster. Woo-hoo! Definitely getting sprayed a little bit, but that's all right. And we're on 12S power now. Woo! Oh yeah, we're just cruising over the waves. Oh yeah. Oh, I was flying for a sec there. Oh man. Okay, we went too high. So wet, everything is wet. Okay, I'm in the more wind sheltered area again. Oh yeah, this is great. Look at that. Oh yeah, I can just ride it. Oh shit, not again. Woo. Even the backs of the holes are basically out of the water. Wow. Oh man, that's too fun. Gently gliding over the surface of the water like this is a pretty magical feeling. If not for any of the efficiency reasons, having a foil is great for just helping make rough water feel smoother. But then again, that only really works at higher speeds, and this hull design is really not optimized for speeds this fast. So maybe the hydrofoil would be more practical on a planing hull, I don't know. But it sure as heck is fun to mess around with. The fastest I was able to go with the foil was around 23 kilometers per hour, or 14 miles per hour. That's the speed at which it would make too much lift and breach the surface. After messing around with foils for a while, I took it off and measured the full throttle speed on 12S. Holy shit. 28 kilometers per hour. Holy shit. That's 17.4 miles per hour, which is 3 times our hull speed. That was crazy. This thing's got some power, man. Crazy. 28, same speed. This is way faster than I ever expected this boat to go. Again, not the right hull design for high speeds. I'm just having fun here. But now we know hydrofoils can really help with ride smoothness at high speeds, and I have an idea of what propellers work best with this boat. So all in all, I'd say that was a productive few days of work. By the way, if you want to check out the log data from the Megan, I'll put a link to it in the video description. In the next video of this boat, I'm going to be doing a long distance mission, so stay tuned for that. Thanks for watching, bye. But wait, if you bought a color shadow lamp, don't forget to unlock high power mode through the web UI. I would hate to have a bunch of people not getting the max performance out of their lamp, but be careful not to let the LEDs get too close to anything because they do make some heat. Fun fact, high power mode is still only 60% of the max current that these LEDs are rated for, but at 100% current they just get way too hot and trip the thermal cutoff switch after 30 seconds or so. Big thanks to everyone who bought one of these. The first batch recently sold out, so it's been a big success. The second batch is on its way, so if you want one you can pre-order it now. I'll leave you with some nice drone footage. Thanks for watching, bye again. What in the hell is that thing? I didn't know you could buy a water car. That's pretty funny. Oh, look at that. It's got an outboard. 100 horse. That thing is hilarious.